Awesome. So I'm going to kind of expand on Abby's introduction to logistic regression. So that. So over the next several weeks, we're going to be focusing on a special type of model called a generalized linear model. So next week, we're going to talk about ordinal regression, and I think Faustine is going to spearhead that particular discussion. Then we're going to talk about multinomial regression. Then after spring break, we're going to talk about Poisson regression. So we're going to be really acquainted with the generalized linear models, in the next several weeks. So today we're going to talk about binary outcome models, and we're going to focus on logistic regression. So these are all the packages that you will need to follow along with this lecture. And then you can also click on this link here and you can run the Cordo document in RStudio if you'd like. So today I'm going to be using the WebR applet or plugin, which allows you to run code in the actual web browser. So you actually don't really need RStudio today, but you can follow along if you'd like to write notes. So what I want to do today is I want to kind of talk about the nuts and bolts of logistic regression. So just provide an introduction to logistic regression and kind of extend on what Abby talked about. And then I want to kind of couch this within a particular data set. So I want us to run a logistic regression on a data set, and we're going to talk about how to fit those models, how to interpret the parameters. We're going to talk about model estimation, how to visualize logistic data, as well as report logistic data. So this all should help you prepare for the lab that's on Wednesday. So everything that we've done thus far has included a continuous outcome variable. So in Psych 503, we exclusively use continuous outcomes, and even the few weeks that we've been in this class, we've used continuous outcomes. And what we've generally done is we've modeled that outcome as a linear function of the predictors using our beloved linear model. Right? So we have our y equals b sub 0 plus b sub 1 plus some error. And an assumption of this linear model is that y variable, the outcome variable, is normally distributed, right? With mu and sigma, right? And continuous outcomes make our life really simple. They're very easy to use. They're very easy to interpret. However, in psychology and the social sciences in general, we don't exclusively use continuous outcomes, right? As Abby highlighted, we tend to use dichotomous outcomes a lot. And we also use multi-categorical outcomes a lot, right? So Abby provided some nice examples of dichotomous outcomes, right? There's a whole host of examples. But the main idea here is that what we usually do is we usually kind of dummy code these dichotomous outcomes as 0 and 1, where we want to model the probability of one occurring or selecting one. So the question is can we take those dichotomous outcomes and just throw them in a linear model? So if you're an economist, yes, you would take your dichotomous outcomes and throw them in a model. This is called linear probability modeling. I don't ascribe to that. I feel like we should be fitting our data to distributions that align very well with the data. But some people might want to use a linear model. And there was a paper a couple years ago by someone from Princeton who taught this class before me, who says that you can use dichotomous outcomes in a linear model. I don't ascribe to that. Yeah, Ham?
Funny story to share. So last semester we took a class from what college that department?
Oh yeah, let me guess. Linear probability modeling.
No, not exactly. So he asked a question, what are the assumptions of linear model?
Yeah.
And I said, one of them is normality.
Uh-huh.
And he said, why do you have to assume normality? I was like, maybe not. And I started to question my whole training, my entire life.
What was it?
That happened.
He repressed it. So I mean, again, you don't have to assume normality if you use we're going to talk about generalized linear models, right? But if we're talking about linear modeling, the traditional
linear model, right? He didn't address generalized linear model at all. That was not part of the class.
Interesting. So again, I think that's this framework of this linear probability modeling, right? Where you could take these dichotomous outcomes and throw them in the linear model. I think that's what he was referring to. But yeah, no, people in econ and poli-sci, they ascribe to this model, right? This probability modeling or linear probability modeling, where you can just throw your dichotomous outcomes in a linear model. Again, if that's what you want to do, you can go ahead and do that. I don't think that they're appropriate for linear models, and there's several reasons why I don't think that. And Abby touched upon these, right? So when we have dichotomous variables, right, we're usually modeling the probability of one occurring, right? A success, a yes, a pass, et cetera, et cetera. If we throw that into a linear model, that linear model, remember, is fitting a straight line that goes into positive infinity and negative infinity, right? So when we make predictions from that model, it's very possible that it could extend outside that range, right? So we have 0, 1, that's our bounds. If we fit a linear model, it's possible that we could have predictions that fall outside 0 and 1, right? So I wish I had Abby's picture, but if you remember, kind of, she fit that linear model curve, right? It extended, beyond the actual bounds of the data, right? So it can predict inaccurate values, which is problematic to me, especially when we're working at a dichotomous variable. The other reasons why I don't think it's appropriate relates to assumptions. So the linear model assumes normal residuals. Well, when we have a discrete outcome, right? Yes, no, heads, tails, we're going to get discrete residuals, right? So essentially what we have is the probability of one occurring, we get residuals for that, and then probability of one not occurring. So we're going to get these funky residuals that are not normal. So that's another issue. Heteroscedasticity is another issue where there's non-constant error variance. And what we see is that variance is influenced by P. Abby showed a figure of her data where the actual distribution was kind of moved slightly depending on what the probability was of 0.4 versus whatever the other one was, like 0.5, right? So if you remember, when we have these violations of non-normality and also heteroscedasticity, we have issues with standard error, and thus our hypothesis tests can be biased, which is problematic. So this is why we don't want to use linear models. Again, if you're a political scientist or an economist, do what you want. Do what your field tells you to do. But hopefully I can persuade you that there's other better ways to model these type of data. Yeah, Chris.
So because this logistic is in log R, so when you're using logistic regression, you're not really getting an average treatment effect. But when you do the linear model, you are.
Yeah, so it becomes more complicated when we start talking about logistic regression. There's a thing called G computation that's performed on the logistic regression. So Solomon Kurtz gave a talk last semester on this very issue, but it's a complicated topic. So we're gonna sweep it under the rug. But if you're interested in that, I can send you the recording for that, if you're interested in average treatment effects. So in the linear world, average treatment effects are really easy. In the logistic world, not so easy. So what do we do? Yeah. So what do we do when we can't, throw our dichotomous outcomes in a linear model? Well, we can run what's called a generalized linear model, which is just a generalization or an extension of the linear model that we know and love. We can use a generalized linear model with non-normal response likelihoods or non-normal just response distributions. And there's 3 things that are required. One, we need some type of distribution that fits our outcome variable with some parameters, right? So we can't use the normal distribution with mu and sigma, right? We have to use some other distribution. We need a link function, which I am highlighting here with G. So this basically takes our outcome variable and kind of just modifies it. And then we also need our linear model component, our architecture that we know and love. And what I think is pretty cool is that we can take this link function, right? It transforms the outcome variable to make it linear. So we can actually use the linear model that we know, that we've been learning, that we know, and that we love, right? So that's what the link function essentially does, is it takes our outcome variable that's dichotomous and just makes it linear. So then we can model it as a linear function of the predictors, which is really cool, I think. And in logistic regression, we use a logit link or logic link function. If we were going to use probit regression, we'd use a probit link. But logistic regression uses the logit link function. So as I said, when we're using these generalized linear models, we need to figure out what distribution fits our data, right? So with dichotomous outcomes, with logistic modeling, we're basically wanting to figure out what the probability of responding correctly is, or whatever you coded as 1, right? So we don't know this probability, we want to estimate it from the data. What distribution do we use? So a distribution that's fairly popular and fairly common when we're looking at probabilities is the Bernoulli distribution. And the Bernoulli distribution is just the distribution of a single discrete binary outcome. It's one event, so you flip a coin, you either get heads or you get tails. That is a Bernoulli event. And outcome variables are distributed Bernoulli with just one parameter, and that's probability. And that's the probability of success. And then we know that 1 minus p would be the probability of failure. And what I have here is just to get the mean from a Bernoulli distribution is just probability. And the variance is the probability times 1 minus p. And the standard deviation is just the square root of that. And what I have here are some Bernoulli distributions. So you get a sense of kind of what they look like. Again, it's just one event. If the probability is of 0.2, that means the probability y equals 1 is 0.2, and the probability that y equals 0 is 0.8. If the probability is 0.5, the probability y equals 1 is 0.5, and the probability that y equals 0 is 0.5. And then if the probability is 0.8, the probability y equals 1 is 0.8, and the probability y equals 0 is 0.2. So this is a Bernoulli distribution, and closely related to the Bernoulli distribution is the binomial distribution, which Abby talked about a little bit. And what the binomial distribution is essentially is just a whole bunch of Bernoulli events, right? In this case here, we only have one event. That's why it's kind of hard to see here, but I've kind of crossed out this little tuning knob here, which says n equals 1, because you only have one event here, right? We're only estimating p. And right, tuning the knob will take those bars and kind of shift them up or down depending on what the probability is. With a binomial distribution, we have two parameters now. We have n and p. And n is the number of trials that we have, and p is just the probability, right? So probability of y equals 1. And the mean within this binomial distribution is just n times p. The variance is np times 1 minus p, and then the standard deviation of that is just a square root of that. And what I have here are just examples of two binomial distributions. So on the x-axis, we have students, and let's say that the dichotomous outcome is pass or fail this class. If we have a probability of 0.5 with 10 students, we can see that the distribution looks like this, where the mean is about 5. So 5 students pass this class, 5 students fail this class. If the probability was 0.8 with 10 students, we can see that the distribution is a little different, right? Where now the mean is 8. So 8 students pass this class, and then 2 students fail this class. But what I wanted you to highlight here again is, again, p times n is the mean, and this scales with the variance scales with that probability, where we can see that the distribution has kind of shifted over, right? From when we went from a probability of 0.5 to a probability of 0.8. So again, when we talk about heteroscedasticity, this is what this is referring to, that the probability influences the actual distribution. So,
Wait, sorry.
yeah.
In the mean equation, what is the dollar sign?
Oh, sorry. That's there was an issue with the formatting. So yeah, no, there's no dollar sign. It's just n times p. No weird mathematical equation. So you might be asking yourself, do I fit a Bernoulli distribution? Do I fit a binomial distribution? Luckily in R, as Abby pointed out, there's only one family that you have to specify, and that's the binomial family, right? And then the link equals logit is just the default. However, you can read your data in slightly different ways. One way that I think is the most common way, and the way that we probably read in our data when we're doing these type of things, is the Bernoulli way, or the Bernoulli instantiation. And I have an example of what that would look like here, where in this particular instance, we have an event on each row. So we have a Bernoulli event on each row, whether it's fail or pass or fail, right? You get only one outcome on each row. And I think that this is how we usually read in our data when we're doing these analyses, right? Another way is the binomial way. And this way, our data is set up a little differently. So our data on each row has the number of successes, which would be the number of deaths in this column, and then n equals the number of trials. And what we do is we take this information and read it into our GLM using the cbind function, where we actually have to specify the deaths column, which is the number of successes, and then n minus deaths, which would be the number of, I guess, non-deaths, right? So we're specifying it a little differently, right? Our data is structured a little differently. However, both of these will basically give us the same result. But you might see this in the wild and you might wonder what the heck that is. That's essentially what this means. We're just fitting it a little differently, right? Where we're actually just specifying the total number of successes and the total number of failures, right? And reading that explicitly in.
So the second object kind of like for each participant, if they have like a
Yep.
score.
Yeah, so if you have a participant with, let's say, 500 trials, you would just add up the number of ones and then like put that on the row, right? So like 50 successes or 50, correct responses versus 500 trials, something like that. But so I think that for the most part, we use this Bernoulli instantiation when we're reading in our data like this, but just to be aware of it. So what I wanted to do now is I wanted to spend some time talking about the logic link function and what it's doing. So what the logic link does, again, is it takes our odds, right? We log it, and it makes things linear, right? Well, what we can do is we can actually transform this logic link or this log odds, and we can transform it into a probability. So we can transform it so it's in the probability space. And all we're doing is just taking the exponent of the logit and then dividing that by 1 plus the exponent of the logit. And that gives us probability. And essentially probability is what we want, right? What the heck is log odds anyways? So what I wanted to do is kind of walk through the steps so we can conceptually see kind of this logic link function in practice. So we're going to start off with a probability. So this is the probability that, y equals 1. And we're going to transform that into odds. And odds is basically just the probability of something happening divided by the probability of something not happening. But unfortunately, we can't just take these odds and throw them in our linear model, right? So they don't have nice features. One issue is that they're asymmetric. So this is highlighted here. So if our odds were if the denominator is greater here, our odds fall between 0 and 1. If the numerator is greater, it could go into infinity, right? So that is not a good feature to put into a linear model. And also, as is highlighted here, it's kind of curvy, right? So we don't want to put anything curvy into our linear model. So the solution to this is just take the log of the odds. And the log of the odds solves a lot of problems. So if our odds are less than 1, it turns it into a negative number. So now it makes our data more linear. So now it goes into positive infinity and negative infinity, right? So now we can put this into our linear model. And it also makes the data more symmetric as well, as highlighted here. So again, the log odds conversion allows us to model these things linearly. However, the parameter that we're interested in, right, probability, is between 0 and 1. So the issue is how do we take this log odds and how do we transform it so it's between 0 and 1? So what we're going to do is we're going to actually fit a squiggle function. And that's no, it's not the technical term. It's not a squiggle. It's a logistic or sigmoid curve that we're actually going to fit here. And how we do this, how we transform the data from the log odds to probability space, is using what's called the logistic transform. And we talked a little bit about this, or I showed the equation, but it's basically just the exponent of the logit on the log odds, right, divided by 1 plus the exponent of the logit, right? And this gives us probability. And this gives us, values within this bounds of 0 and 1. So in the context of logistic regression, there's kind of two parameters that we care about as it relates to this logistic function. One is the intercept, and the intercept value is essentially the midpoint of the logistic curve. And it's the point where there is kind of the most growth or most change in probability. And we can see highlighted here that the intercept determines where it falls on this x-axis here, right? So we have higher values of the intercept. We see that it's kind of shifted to the right. Lower values of the intercept kind of shifted to the left. And to draw some comparisons to a linear model, the intercept within a logistic model is basically the value of y when all the predictors are 0. Again, to draw some correlation with linear models here. But the intercept determines where it kind of falls on this x-axis here. The slope determines the steepness of the curve, or how fast the growth is, or how fast the change is, or how drastic the change is. If we have a high slope, we can see that there's a steeper middle portion here, or line portion of our logistic curve. But if we have a lower slope, we can see that it's a more shallower type of growth here. The change is kind of less drastic. So the higher the slope is, the more drastic or the higher changes are going to occur. So these are the two parameters that we're interested in when we're fitting these logistic models, just to draw some comparison. So are there any questions so far?
No, I kind of had a question.
Yeah.
How does this relate to like in the fall when we did like logistic transformations and then like ran a linear model? How's that?
Same thing.
It's the same thing.
Yeah. So that's why I wanted to talk about transformations, because it parallels this.
Okay.
Yeah. So like when we took like just take the log of whatever our variable, right? Yeah. Same
Okay.
thing. Yep. Same thing. So just to kind of summarize, right? So we're interested in probabilities, right? But we can't model those linearly, right? They're too curvy and they're bounded between 0 and 1. We could take the odds, but that still won't work, right? It's still too curvy for linear models. What we could do is we could take the log of the odds, and then this allows us to, put this into our linear model and make inferences. And then we can transform back to probabilities, which I think is super cool. So as you hopefully intuited, there is an interrelationship between probabilities, odds, and log odds, right? So we can go from log odds to probabilities using the logistic transform, or we could go from probabilities to log odds using the logit transformation, right? So these things are all interconnected. And this allows us to, interpret the parameters at different levels, right? We could talk about it in log odds, probabilities, which I think is super cool. So in R, there's a couple functions that allow us to do this. So if we want to go from probabilities to log odds, we could use the qlogis function, right? And just put in the probability. If we want to go from log odds to probabilities, we use the plogis function. And this will give us a probability based off of the log odds that we put into the function. So this is just the visualization of how these things are related to one another. So here we have the sigmoid curve here, right? And log odds are on the x-axis, and we have probability on the y-axis. We see that a log odds of 0 is associated with a probability of 0.5 and an odds of 0.1. So again, I think it's important to understand the relationship between all these things, especially when interpreting coefficients, to get a sense of kind of the scale and magnitude. So now I wanted to talk about model estimation a little bit. So when we're fitting a regular regression model, right, we're trying to figure out the best fit line, right? And we are trying to find the line that minimizes the sums of the squares, right? Well, we're kind of doing the same thing in logistic regression, but we're not trying to find the best fitting line. We're trying to find the best fitting squiggle. And we don't use sums of squares in logistic regression. Instead, we use our good friend maximum likelihood estimation to figure out what that best fitting squiggle is. And here I just wanted to kind of highlight with visualizations kind of conceptually what's going on, right? So we have these dichotomous outcomes, right? We have zeros and ones, passes, fails. And essentially what we're doing is we're just figuring out where those dots lie on this line here, this linear line here, right? And then what we can do is we can actually transform these into a probability. And then from this, we get our nice little sigmoid curve, right? And remember that maximum likelihood is this iterative process. We're doing this lots and lots and lots of times. So again, this is kind of, a cartoony example here, but we're just fitting a whole bunch of squiggles and we're trying to find the squiggle that maximizes the likelihood of the data. And once we figure out the best fitting curve, then we get our slopes and we get our intercept values from that squiggle line. So this is what's kind of happening in a nutshell in terms of maximum likelihood estimation and logistic regression. So are there any questions about kind of the basics, nuts and bolts of logistic regression? Anything? So now I want to spend the rest of the time applying logistic regression to a data set. So the data set that we're going to use contains a sample of 500 teens. And this was collected through this US Youth Risk Behavior Surveillance System survey. And we want to answer two questions here. The first question we want to answer is, are the odds that young females report trying to lose weight greater than the odds that males do? And the second question is increasing BMI associated with an interest in losing weight, regardless of sex? So those are the two questions we're going to try to answer with our data set. And we're going to use the WebR code chunks, and this allows us to run our code in the actual browser itself, so you guys can follow along in the actual browser along with me. So let's go ahead and just run this code chunk here, and if you are successful, we can load in the data set. Let's see what it looks like. So we should see something like this, where we have all of our variables. So if you successfully ran that code chunk, you should see something that looks like this. What we're interested in are several variables from this data set. So one of the variables that we're interested in is this lose weight 01 variable. So 1 is coded as someone who indicated they're trying to lose weight, 0 is trying not to lose weight. And we're going to be looking at two predictor variables, sex and female. So 0 is coded as male and 1 as female. And then we're also interested in this BMI variable, which is just a percentile for a given BMI. So those are the variables that we're going to look at. And the important first step in any data analysis is to visualize our data. So what I have highlighted here are just two different interpretations of the relationship between losing weight and sex. So here on the left-hand side, right, we just have bar plots with count on the y-axis here. So what can we glean from this particular visualization in terms of the relationship between losing weight and sex? So 0 is not wanting to lose weight and 1 is the desire to lose weight. What do we see in terms of differences between males and females?
The women want to lose weight and men don't.
Yeah, that's essentially in a nutshell. That's what the data is showing, right? So this is one way that we can visualize the data. I think a better way to visualize the data is the visualization on the right-hand side here, where we have these stacked bar plots. So if we're going to visualize categorical data and look at percentages, I think that this is a good way to visualize those things, where we have the actual percentages in the bar plots. So this tells the reader what the actual percentage is, or what the actual probabilities are between males and between the actual categories themselves, right? So we can clearly see here that males report wanting to not lose weight more than lose weight versus females who report wanting to lose more weight than not lose weight. We can also look at the relationship between BMI and whether they want to lose weight or not, or individuals want to lose weight or not. So what can we see from these histograms? So an increase of BMI is, verging on, closer to like obesity and being in the higher, danger range. Anyone want to take a guess?
It's people with a high BMI want to lose weight.
Yeah, yeah, essentially, yeah. People with a high BMI usually report wanting to lose weight, whereas individuals, it's kind of uniform almost when individuals say that they don't want to lose weight. It seems like BMI doesn't really have an effect on that.
Like, set us up, there's this uniform
Yeah.
on no weight loss.
Yeah.
Shouldn't it be like the opposite?
Yeah, no, I mean, again, so you're saying like higher frequencies, like on the lower end of the spectrum,
Yeah.
right? Yeah, I think that is plausible, but the data is what the data. So we can also look at this relationship, faceted or grouped by whether individuals want to lose weight or not, and also by sex. So what can we interpret from this particular visualization? Do you think that there's any gender differences or sex differences here?
Not too much.
Nah. It seems like in general that higher BMI individuals report wanting to lose weight more. And it doesn't seem like there's a difference between males and females, which is interesting. So let's test this statistically, and let's go ahead and start fitting some models, right? So we can't just make inferences based off of our visualizations, unfortunately. So let's test this statistically. So what I want to do is kind of do this in a stepwise manner where we're going to fit progressively more complex models and then go over how to interpret those parameters. So as a first step, let's just go ahead and fit an intercept only model. And that's what this mathematical equation is highlighting here, right? We're going to do the logit of the probability, and we're going to estimate the intercept value here. And we can easily fit that model using our GLM function, right? So this is the model formula, right? Where we're going to do lose weight 0, 1. And then this is just saying to estimate the intercept, this one value. So let's just go ahead and run it. But what I'm going to do is I'm going to change just a little bit of code here. And I'm just going to run the actual output or output the output. So when we run this model in R, we get all this output, right? So on the top, we have our GLM formula. We have our coefficients here. We just have an intercept. And what I wanted to highlight here are these null deviance and residual deviance values here. Again, we're fitting this with maximum likelihood estimation, right? So we get deviance values. Does anyone remember what the deviance is?
-2 times log.
Likelihood, yep, correct, yep. So that's what these values essentially represent. The null deviance would be the deviance for a model with no predictors, and our residual deviance would be a model with all of our predictors here. So why are these two the same? So they're both 611.93. Why would they be the same in this model? So if the null deviance is the deviance for a model with no predictors, what model are we fitting here? Yeah, we're fitting a model with no predictors here, so they should be the same. So that's good. Everything is good. So let's go ahead and just run that model here. So this is kind of a truncated output where we have our intercept value for the model, our estimate. And then we can also get standard error and a statistic and a p-value here. Similarly to other models that we've run, right, we're testing two hypotheses. The null hypothesis is that the coefficient is 0, and the alternative hypothesis is that the coefficient is not equal to 0. And the test statistic that we're using here is called a Wald z-test, which is the difference between the actual estimate and 0. And we can get a Wald z-score here by just taking the slope or the intercept estimate and subtracting 0 from it and dividing by the standard error. And this is distributed as a normal distribution, right? Because it's a z-score. And if that value is greater than 1.96 or less than negative 1.96, we can say we have a statistically significant effect, right? That's essentially what we're testing here. And the calculation of the confidence intervals is similar to how we've calculated the confidence intervals in the past. So nothing new there. But just know that with these type of models, we're using this Wald Z statistic. Some other folks use other things, but what's outputted in this particular function, the GLM function, is the Wald statistic, just so you know. All right, so let's go ahead and interpret our intercept value. So we have an estimate of negative 0.21. Right, we need to remember that we use this logit link function, right? So this is the log odds, right? So the intercept is in the log odds metric. So how we can interpret this, because there is no other predictors in the model, just the intercept, is the log odds of y equals 1 or wanting to lose weight is negative 0.21. So that's how we interpret that. But the log odds are kind of hard to interpret, right? So we can actually take this and convert it into a probability. And we can do that by using this logistic transform that I talked about, which is just the exponent of B0 divided by 1 plus the exponent of B0. And we get a value of 0.45. So how we can interpret this intercept value is that the overall probability of students wanting to lose weight is about 45% in our data set. If you're not convinced, we can actually calculate this with our data set. So what I'm doing here is I'm just taking the count of this lose weight function, or excuse me, this lose weight variable, which is basically counting the number of zeros and the number of ones. And we're getting the proportion of those zeros and ones. So we get something like this. So in our data set, there's 246 zeros and the proportion is 0.55. And then there are 199 ones and the proportion is 0.45, which is what we calculated from our model. So we can actually do this with the p-logis function as well. That takes a log odds and transforms it into probability. So we can just read in our intercept value here and we get, again, 0.45, 45%. So this is how we interpret our intercept value when there's no other predictors in the model. Right. So now let's make things a little bit more complicated and let's go ahead and add in a categorical variable into our model. So this female predictor variable is dummy coded. 0 is male and 1 is female. So let's go ahead and run this model here. So you can see that we have a different model formula now where we've added in our female predictor. So let's just go ahead and run that. All right, so if we look at the output of our regression, we have our intercept value, and then we have our predictor value, which is going to be our slope value here. So in the context of this female predictor variable, how do we interpret our intercept value in this case, right? Anybody want to take a shot? What does this negative 0.75 represent?
Wanting to lose weight if, well, it's tricky because it's a binary predictor.
So the intercept is the value of y when x is 0, right? So
but
similar.
0 is just male.
Yeah.
Oh, okay.
Yeah. So that's yeah. So the intercept is basically here in this case is the value or the log odds of y equals 1 or wanting to lose weight when female equals 0 or males. So this is the log odds of y equals 1 for males, right? We could say is 0.75. So that's our log odds value here. We could transform this into a probability, right? So how would we transform this into a probability to make it a little bit more interpretable? What function would we use? What was that again? Yep, or p-logis, close enough. So yeah, so we can take our log odds and we can use this p-logis function. And this will give us the probability, right? So instead of interpreting this in the log odds, we interpret it in the probability space now, right? So 0.32, 32% of individuals. So 32% of males report wanting to lose weight in our data set. So that's how we interpret the intercept value when we have this categorical predictor. How do we interpret the slope estimate, B1? So if X is a categorical predictor, what that slope represents is just the difference in the log odds between group X, which is female, and the baseline, which is male. So let's go ahead and run that model. So we get an estimate of 1.09 in the log odds unit. So how do we interpret that? Basically going from men to women, right? A 1 unit increase. There's a change in the log odds of wanting to lose weight of 1.09. So what we can do with this value, because log odds are kind of hard to interpret, right, is we can actually transform this into an odds ratio, which is reported quite often in the social sciences. And this is basically just taking the log odds and then exponentiating it to get the odds ratio. And what is the odds ratio? Is the relationship between the dependent variable, so wanting to lose weight, and that predictor variable. And with the odds ratio, what we're doing is we're taking the odds, right, the probability of wanting to lose weight divided by the probability of not wanting to lose weight for females, dividing that by the probability of wanting to lose weight by not wanting to lose weight for males, right? And this gives us kind of a multiplicative kind of interpretation of the results here. So we can interpret this as the odds of Y for group X are expected to be the odds or the exponent of the B1 parameter times the odds of Y for the baseline group. And when we look at odds ratios, if the odds is greater than 1, we can say that the event is more likely. If it's less than 1, we say that the event is less likely to occur. And then if the odds is just 1, the likelihood of the event does not change. So do you remember the relationship between probabilities and odds and log odds? So if we have an odds ratio of 1, what does that relate to in terms of probability? Yeah, 50%. So yeah, it doesn't change. The likelihood doesn't change. So what's often done is we usually transform these odds ratios and talk about them in terms of percentage increase and decrease, again, to just make it a little bit more intuitive. And we can easily do that by just taking the odds ratio and subtracting 1 from it, and then multiplying it by 100. And that'll give us a percentage increase or decrease in the odds. So let's go ahead and do that with our actual data and our slope estimate here. So the tidy function allows us to input an argument called exponentiate, and we can set this to true. And this will give us the results on the odds ratio scale, including our confidence intervals if we want to output those confidence intervals. This is from the Broom package. So we use that quite frequently last semester, and we can use that here for our logistic regression. So here we get an odds ratio of 2.98 for this slope parameter. So how do we interpret that parameter? We can say that the odds of wanting to lose weight in females is almost 3 times the odds of wanting to lose weight in men. And we can also talk about this in terms of an increase in percentage, right? So the odds of females wanting to lose weight are 198% higher than the odds of males wanting to lose weight. So this is how we would interpret an odds ratio in the context of our model here. We can also talk about this in terms of predicted probabilities. So what we can do is we can get the probability that males report wanting to lose weight and females want to lose weight. Right? We kind of already did that with the intercept value, right? By taking that log odds and transforming it into a probability. But I wanted to show you how we can do this for females as well. So what we're going to need is we're going to need our intercept value and our slope value from our model. And then what we can do is we can use P-logos again and get our predicted probabilities. So for the males, all we are doing is basically putting in the intercept value, right? So B1 times 0 is going to be 0. For women, what we need to do is we need to introduce the intercept value into our equation. We can't just put in B1. This is going to give us the incorrect predicted probability because this is comparing something to 0. So we need to include the intercept value. And this is a very simple case. When we have lots of predictor variables, we'll need to include those variables as well. And things can get really complicated really fast here. So this is a very simplified version of this. But in order for us to get these predicted probabilities, we need to make sure we include all the information from our model. For women, we need to include the intercept value. So if we run the P-logos function on both, what we get is 32%, which is what we calculated already from our intercept summary report. And then the predicted probability for females in our data set is 0.58, so 58%. Yeah.
Are you putting the intercept in both of them?
Well, so yeah, so but this cancels out essentially. So you're basically just getting the intercept value.
Right.
Yeah, because it's coded as 0.
Yeah.
But yeah, so it'd be the same thing. So we could do this by hand, or we can use our beloved m-means to do this for us, which is what I recommend us doing. So with the m-means function, we can put in our model that we fit and then our predictor variable, and then type equals response gives us the output on the probability scale. So again, we calculated this by hand, but this will give it to us, right? So 0 is 0.32 and 1 is 0.58, so males and females, right? Awesome. And then also what's cool is that we can get our odds ratio. So when we have one predictor variable, we can just use the summary output. However, if we have lots of categorical predictors, lots of continuous predictors, things can become really complicated. So we can use this pairs function, and it will give us the odds ratio for the comparison between females and males, which is 2.98, which is what we saw in the output here, right? So 2.98. But we can get it from amines as well. So it's quite common in the social sciences and in psychology in particular to report odds ratios and the log odds, right? That's primarily what you see in papers. But what we really care about are probabilities. So we can also talk about these things in the probability space. So we can actually calculate the difference in probabilities and report that instead of log odds and odds ratios. This is called the risk difference. And what we can do is we can calculate these things called marginal effects, which looks at changes on the probability scale. So a change in probability in the outcome for a change in the predictor variable. And these are sometimes called average marginal effects. And for categorical variables, it's just basically the difference between the groups, right? So the probability difference between the groups. So we could do this with amines, but it's a little bit more complicated. As I stated, I'm trying to use marginal effects more because I think it's flexible and it can do a lot of stuff. And it can give us these average marginal effects in just one line of code, which I like. So we're going to use this average comparisons function here, and we're going to just do the difference. And it's going to basically give us the difference in probability between males and females, which is 0.26. And then it also gives us, statistics and p-values that we could report, right? So we might not want to report log odds or odds ratios. We could report the actual probability difference, which might actually be more intuitive, right? So this tells us that females are 26% more likely to report wanting to lose weight than males. I think that's pretty, concrete, right? Instead of, a 1.5 change in the log odds. I don't know. So just keep that in mind that we can also talk about these things on the actual probability scale and do inferences based off of that. All right, so now let's add a continuous predictor into our model. So we're going to fit another model, but here we're just going to look at BMI, and we're not going to look at the female predictor variable. Let's go ahead and fit our model here. Again, I'm just replacing female with BMI. So let's go ahead and look at the model that's produced. So this is the output for the model where we have our intercept value and then we have BMI. So let's go ahead and interpret the intercept and the BMI slope parameter here, since we know how to do those now. So how do we interpret the intercept value here with a continuous variable? Yep. The log odds of y equals 1, yeah. So when BMI is 0, and we should probably center this variable since I don't think you can have a BMI of 0, but for interpretation, when BMI equals 0, the log odds of wanting to lose weight is negative 2.57, right? We can also transform this into a probability. So what would that probability be if we were to transform that? Someone want to do that calculation for me? You could just use the code chunk underneath there to run it. 0.07. So we can say that the probability of wanting to lose weight when BMI equals 0 is, you said 7%? Is 7%. So fairly low. And I think that kind of makes sense, right? Because I think that if you have a BMI of 0, you're probably not wanting to lose weight, I don't think. You're probably wanting to gain more weight. So that makes sense. So how do we interpret this BMI term, our slope estimate here? So it'd be very similar for a continuous predictor and a regular regression model.
For like a unit increase in BI, how much like more log odds you will
Yep.
want to lose weight.
We can say the change in the log odds is 0.03, right? So that's how we would interpret that. We're not going to calculate the probability because it becomes a little complex when we're talking about a continuous predictor. We'll talk about this when we talk about marginal effects for this variable, but we'll leave it at that. So what is the odds ratio for B1 here? So how do we get the odds ratio for B1? And how do we interpret that? So someone tell me how I can transform 0.03 into an odds ratio. Guide my fingers on the keyboard. So we take the exponent of that value, and that gives us the odds ratio for that particular estimate. So how do we interpret this? We can say for a unit increase in BMI, the odds are 1.03 times, or so the odds of wanting to lose weight is 1.03 times the odds of not wanting to lose weight. We can talk about this in terms of percentage increase or decrease, right? So this is actually a 3% increase. So we can say that for a unit increase in BMI, right? There is a 3% increase in the odds of wanting to lose weight. So that's how we would interpret an odds ratio for a continuous variable. So are there any questions so far? We could also do the same thing for the intercept as well. And this would give us an odds ratio of less than 1, which makes sense given the information that we have, right? Especially if BMI equals 0. So we could also calculate an odds ratio for the intercept as well. Yes.
How do you interpret interactions for this kind of thing?
So interactions are very complicated in the context of logistic regression. So we're fitting an interaction in this data set, but it's not significant. But we can interpret them in a very similar manner that we would in a regular linear model. So we could talk about these things in terms of probability, or we could talk about interactions in the log odds, right? So in the log odds, the interactions can be interpreted similarly to a linear model, right? Where we can take the simple slopes. But it becomes very complicated, especially when we're going back and forth between log odds and probability, right? Because you can have an interaction in the probability scale, but not in the log odds, and vice versa. So it becomes complicated. But if you're interested in that, I can definitely give you some resources, but it's a complicated topic that I didn't really want to go into. So we're going to put that underneath the rug and not talk about that. So we can also calculate the marginal effects for our continuous variable. So it's a little trickier when we have a continuous variable because we're looking at the instantaneous rate of change in the probability, right? Because it's continuous over a range of different values. So basically what we do is we just calculate the change in the predicted probability for a small change in X. And we can use this average slope functions that will do this for us. But essentially what it's doing is just for each row in our data set, it's just calculating small differences and calculating the predicted probability and then averaging over all of those little small changes. So we get this estimate here, which is the average marginal effect, which is 0.007. And we can change this into a probability, right? So we can say that an increase in BMI results in the 70% increase in the likelihood of wanting to lose weight. So again, makes these things a little bit more concrete. So now let's go ahead and add in, let's go ahead and create models that look at the main effects. So just looking at female and BMI, and then also the interaction between these two things. So let's go ahead and fit those models here. And just as a reminder here, these are all the models that we fit thus far. So fit 1 just included our intercept only. Fit 2 included just female. Fit 3 included just BMI. Fit 4 included both female and BMI, so our main effects model. And then Fit 5 included the interaction between BMI and female. And as you'll notice here, the confidence intervals cross that 0 boundary here for the interaction. So do we include an interaction in our model? We can test this with our likelihood ratio test that we've been using. So what we could do is we could look at the main effects model compared to the interaction model, and we can look at our chi-square statistic. So what do we infer from this? Do we include the interaction model or do we get rid of it? I guess think, what? Yeah, you get rid of it. Why would we get rid of it? Yep. Exactly. Yep. So we're going to get rid of that interaction from our model because it doesn't seem to be adding anything, right? It's just adding complexity, as Kennedy said. So going back to our original questions, so are the odds of females wanting to lose weight greater than the odds of males wanting to lose weight, given what we just went over? Yeah, right. And does increases in BMI lead to increases or a greater probability of wanting to lose weight, regardless of sex? Right? There wasn't any interaction between the two, right? So it doesn't seem like sex really matters. An increase in BMI seems to lead to a greater likelihood of wanting to lose weight. So we can answer our questions that we proposed at the beginning. Yeah, Chris.
So our estimand is different for these, right? And so do you have any advice for how to think of like an average marginal effect in writing about that as compared to an average treatment effect that we're usually writing about when we're writing like linear? They seem like there's different interpretations.
Let me get back to you on that one. So again, it's kind of complex. And it's something that I didn't really want to highlight because of how complex it is. But I'll get back to you on that with an actual answer. Let me get through some of this stuff first. So the model that we're going to go with is our main effects model, right? With female and BMI. So I wanted to talk a little bit about model fit. So how good is our model? So when we're fitting a linear model, right, we can look at R squared, and we can use our sums of squares to calculate an R squared measure. In logistic regression and things with maximum likelihood, we can't use sums of squares, so we calculate these things called pseudo R squareds. And there are a whole host of different pseudo R squared measures. And one of them that's quite commonly used is called the McFadden's R squared. And the McFadden's is fairly easy to calculate, which is why I'm highlighting it here, where you just take the deviance of the residual in the summary output and divide it by the null deviance, and then subtract 1, and that gives you the R squared. And Easy Stats has a function called R squares McFadden, and it gives you the R squared and also the adjusted R squared here. Again, as I said, there's a whole bunch of other types of R squared measures that we can use. Easy Stats by default uses this Tours R squared. So when you run the report function, it'll output that particular R squared. But McFadden's is fairly common and popular. One thing that I wanted to highlight here is that when we're talking about pseudo R squared, we're not talking about explained variance, but we're just looking at R squared as a model fit measure, or how good our model is, with higher values of R squared, meaning better fit. Here, an R squared of 0.24 is fairly high. So we can say that the fit is pretty good. We can also look at residuals to determine our model fit. So as Abby pointed out, we can't just look at normal residuals, right? Because we'll get something wonky like this. Our outcome is discrete, right? So we're going to get these discrete residuals. So what's been suggested is this thing called binned residuals. And bin residuals are calculated by first taking the raw residuals, right? So taking each observed value and subtracting the predicted value from the fitted line. And then what we do is we order our observations. So it could be probabilities of the DV or our predictor variables, and we create equal sized bins. And then within those bins, we just average the residuals, and then we can plot those residuals, and we'll get something that looks like this. And what we want is for these residuals, these points, to fall within these boundaries here. These are like standard error boundaries, right? We want all of our points to be kind of distributed uniformly along this line and not outside these boundaries, because that would be indicative of a poor model fit. So this is one way to get around this whole non-normal residuals thing. And similarly to other kind of residual plots, we want to look for patterns in the actual binned residuals. And if we see things like the residuals kind of going up and then down, this might be indicative of a nonlinear pattern, right? That we might need to transform our predictor variable, right? So it's important to look at these binned residual plots, right? And this goes along with this linearity assumption. So we want to look at these binned plots to see if there's any patterns in the data and make changes accordingly. We also want to look to see if there's really large residuals with large magnitudes that fall outside of these boundaries. This could be indicative of a poor model fit where we're not accounting for certain predictors or maybe like an interaction variable. So again, it's important to look at these bin residual plots, and they tell us how good the model fit is. So generally speaking, like if we see something like this, that means our model fit is pretty good. So I want to spend some time talking about visualizing our data. So we can visualize our data on the logit scale or the log odds scale, right? That's linear, but it's quite common to look at these things in terms of predicted probabilities. So this is an example of one way that we could actually visualize our data, right, on the probability scale, where we're looking at females and males as a function of BMI. And what's important to note is here, again, is that, again, there's no interaction in our model, right? These curves are pretty similar to one another, right? So this is one way that we could visualize the data. There's a whole bunch of ggplot code underlying this that you can see in the Cordo document. But we could use ggfx, and then in 2 lines of code, we can get something like this. And this is what I suggest we visualize, where we actually visualize the actual discrete data, right? Our zeros and ones, and then also the predicted probability here. So I think that this particular figure looks pretty nice. So this is for continuous variables. If we were just working with categorical variables, I would suggest something like this. So like something like this with the predicted probabilities within the bar plots or the box plots. So if we're just dealing with strictly categorical variables, suggest something like that. So I want to talk a little bit about assumptions of logistic regression. There's not many of them. One assumption is that the outcome is dichotomous. That's fairly easy to check, right? The other assumption is that observations are independent, but that could be easily solved if they're not, by just fitting a generalized linear multi-level model. And then also there's an assumption of linearity, but in the log odds. Again, it's not going to be linear in the probability space, but linearity in the log odds. Normality assumptions and homogeneity variance are not usually checked, right? Because those are violated. We can easily check our assumptions by using our check model function. So with the check model function, we can output a binned residuals plot that looks like this. So this looks pretty good. This does this as a function of the actual DV. But what I would suggest is to also look at the bin residual plots for our predictor variables as well. And this could be indicative of some type of non-linearity in the model. So we just don't want to look at the DV. This is an indicator of how good the model fit is, right? So all of these little points fall within this standard error, these bounds here. So this looks pretty good. We can also look at our observations or influential observations. So are there any outliers in our data? So we can output that particular check, and then also collinearity check as well. So these are all the tests that we'd want to perform on our data. So we can easily fit a table to our results by using model summary. Don't need to go over that too much in detail. This is just for the lab on Wednesday. And then lastly, what I wanted to talk about is reporting logistic regression results. So this is an example of how we can take the report function and weave it in to something that's human readable and not something that sounds really clunky. So what I've done is I've taken the input from report and just kind of added it into the pros of reporting. So I said we fitted a logistic model with a logic link with sex and BMI predicting desire to lose weight, and I included the formula here. So the model's explanatory power is substantial. So as I said, they used the Tours R squared, which is 0.3, which is a little higher than the McFadden's R squared. The probability of females wanting to lose weight was 33% higher. So that's our marginal effect, right? And then what I have in the statistical part is the log odds and the odds ratio. So my suggestion is that in the actual body of the text, we talk about probabilities, right? And then we supplement that with our statistics like log odds and odds ratios. I just think that probabilities make a little bit more sense than log odds and odds ratios. I then say that an increase in BMI was associated with an increased probability of wanting to lose weight. So we have our log odds and our odds ratios along with our 95% confidence intervals. And then I said, looking at the average marginal effect, the 1 unit increase in BMI was associated with an 80% increase in desire to lose weight. So this is just a little example of how we should write up our results for a logistic regression. The textbook chapter also has a sample write-up of a logistic regression that I would look at for a lab on Wednesday. So with that, that is all that I have, just right on time. So for Wednesday, read the textbook chapter on logistic regression. It will definitely help you in completing the lab for Wednesday. So are there any questions, comments about logistic regression? You guys ready to run your own logistic regression on Wednesday? Yeah, okay. Shouldn't be too difficult. But with that, you guys are free to go if you don't have any